conclusion that a number 1 copper conductor came loose and caused a failure is plausible. There are several potential issues with the installation that could have contributed to the failure. Firstly, copper and aluminum conductors have different electrical properties and cannot be directly connected without using a compatible connector. The split bolt connector is not recommended for connecting copper and aluminum conductors, as it does not provide a reliable, long-lasting connection. Secondly, split bolt connectors must be properly torqued to ensure a secure connection. If the connector was not torqued correctly, it may have loosened over time, causing the number 1 copper conductor to become loose. Thirdly, over-tightening the split bolt connector can damage the conductors and weaken the connection. Fourthly, antioxidant grease is used to prevent corrosion and improve the connection between dissimilar metals. If antioxidant grease was not used, it could have led to corrosion and a weakened connection. Fifthly, the connection was installed in a gutter, which is exposed to moisture and temperature fluctuations. These environmental factors could have degraded the connection over time. There are other possible causes as well. The conductors could have been damaged during installation or handling, weakening the connection. A temporary overcurrent fault could have caused the connection to overheat and fail. However, it is unlikely that the failure would have occurred without any devices tripping. To prevent similar failures in the future, one must use compatible connectors for connecting different types of conductors. Secondly, properly torque all connections according to manufacturer's specifications. Thirdly, use antioxidant grease on connections between dissimilar metals. Fourthly, protect connections from environmental factors such as moisture and temperature fluctuations. Fifthly, regularly inspect and maintain electrical connections to ensure proper operation. Electrical connections are the backbone of any electrical system, ensuring the safe and efficient transfer of electrical energy. However, when these connections fail, they can lead to a variety of problems ranging from minor inconveniences to serious hazard. Understanding the causes of electrical connection failures and implementing preventive measures is crucial for maintaining a reliable and safe electrical system. Incompatible conductors are a common cause of electrical connection failures. Copper and aluminum, two of the most common conductors used in electrical systems, possess different electrical properties. When directly connected without proper precautions, these dissimilar metals can create a galvanic reaction, leading to corrosion and a weakened connection. To avoid this issue, always use connectors specifically designed for connecting copper and aluminum conductors. These connectors typically feature a barrier that prevents direct contact between the two metals, minimizing the risk of corrosion. Improper torquing is another frequent culprit behind electrical connection failures. Connectors, such as split bolt connectors and terminal screws, must be tightened to the manufacturer's specified torque to ensure a secure and reliable connection. Under-tightening can result in a loose connection, increasing resistance and generating heat, which can eventually lead to failure. Over-tightening, on the other hand, can damage the conductors or the connector itself, compromising the connection's integrity. Always use a calibrated torque wrench to tighten connectors to the correct torque value, and consult the manufacturer's instructions for specific torque recommendations. Environmental factors can also play a significant role in electrical connection failures. Moisture, temperature fluctuations, and corrosive atmospheres can all degrade connections over time. Moisture can promote corrosion, while temperature fluctuations can cause expansion and contraction, leading to loosening of connections. Corrosive atmospheres can accelerate the degradation of conductors and connectors, weakening the connection. To protect connections from environmental factors, consider using weatherproof enclosures or applying corrosion-resistant coatings. Regular inspection and maintenance are essential for preventing electrical connection failures. Regularly inspect connections for signs of corrosion, loosening, or damage. Use thermal imaging to identify hotspots, which may indicate loose or corroded connections. Retorque connections as needed, and replace any damaged or corroded components. Proper maintenance can help identify and address potential problems before they lead to failures. Additionally, overcurrent faults, though less common, can also contribute to electrical connection failures. A temporary overcurrent, such as a surge or short circuit, can cause a connection to overheat and fail even if the overcurrent protection devices do not trip. To mitigate this risk, ensure that the electrical system is properly protected with appropriately sized fuses or circuit breakers. Furthermore, consider using surge protection devices to protect sensitive equipment from voltage spikes. Selecting the right type of connector is crucial for establishing a reliable electrical connection. Different types of connectors are designed for specific applications and conductor types. For example, compression connectors are often preferred for connecting large conductors, while twist-on wire connectors are commonly used for smaller wires. Always choose connectors that are specifically rated for the conductors being connected and the intended application. In addition to selecting the right connector, proper installation techniques are essential for ensuring a secure and reliable connection. When stripping the insulation from conductors, avoid nicking or damaging the wire, as this can weaken the connection. When connecting wires, ensure that they are properly aligned and inserted fully into the connector. Tighten connectors securely, but avoid over-tightening, which can damage the conductors or connector. Furthermore, using antioxidant grease on connections between similar metals, such as copper and aluminum, can help prevent corrosion and improve the connection's conductivity. Antioxidant grease creates a barrier that prevents moisture and air from reaching the metal surfaces, minimizing the risk of corrosion. Apply a thin layer of antioxidant grease to the conductor before inserting it into the connector. Regularly inspecting and testing electrical connections can help identify potential problems before they lead to failures. Visual inspections can reveal signs of corrosion, loosening, or damage. Thermal imaging can detect hotspots, which may indicate loose or corroded connections. Insulation resistance testing can assess the integrity of the insulation surrounding conductors and connections. By conducting regular inspections and tests, potential problems can be identified and addressed before they escalate into costly and dangerous failures. Protecting electrical connections from physical damage is also crucial for maintaining their integrity. Securely support conductors and connectors to prevent them from being subjected to excessive stress or strain. Avoid running conductors through areas where they may be exposed to physical damage, such as walkways or loading docks. If conductors must be run in such areas, provide adequate protection, such as conduit or cable trays. Furthermore, proper grounding is essential for preventing electrical shock hazards and ensuring the safe operation of electrical equipment. Grounding provides a low-resistance path for fault currents to flow back to the source, allowing overcurrent protection devices to trip and de-energize the circuit. Ensure that all electrical equipment and systems are properly grounded in accordance with applicable codes and standards. Documenting and tracking electrical connection maintenance can help ensure that connections are regularly inspected and maintained. Maintain a record of all electrical connections, including their location, type, and date of installation. Schedule regular inspections and maintenance, and document any work performed. By tracking maintenance activities, potential problems can be identified and addressed proactively, minimizing the risk of failures. In conclusion, electrical connection failures can have serious consequences, ranging from minor inconveniences to major hazards. By understanding the causes of these failures and implementing preventive measures, one can ensure the safe and reliable operation of electrical systems. Use compatible connectors, torque connections properly, protect connections from environmental factors, and regularly inspect and maintain connections. By following these recommendations, electrical connection failures can be minimized, ensuring a safe and efficient electrical system. Additionally, ensuring proper conductor sizing is crucial for preventing overheating and potential connection failures. Conductors must be sized appropriately to handle the anticipated current load. Undersized conductors can overheat, leading to insulation damage, connection failures, and even fires. Consult the National Electrical Code, or NEC, for guidance on conductor sizing based on ampacity and other factors. Overcrowding of conductors in enclosures can also contribute to overheating and connection failures. When conductors are packed too tightly together, they can trap heat, leading to elevated temperatures. Ensure that enclosures are adequately sized to accommodate the number of conductors and connections, providing sufficient ventilation to dissipate heat. Furthermore, using the correct type of wire termination is essential for establishing a secure and reliable connection. Different types of wire terminations are designed for specific applications and conductor types. For example, crimp-on terminals are often preferred for connecting stranded conductors, while screw terminals are commonly used for solid conductors. Always choose wire terminations that are specifically rated for the conductors being connected and the intended application. When making wire terminations, ensure that the insulation is properly stripped and the conductors are fully inserted into the terminal. Tighten terminals securely, but avoid over-tightening, which can damage the conductors or terminal. Additionally, using a proper crimping tool is essential for establishing a secure and reliable crimp connection. Crimping tools are designed to compress the terminal onto the conductor, creating a gas-tight seal. Use a crimping tool that is specifically designed for the type and size of terminal being used. Over or under crimping can result in a weak or unreliable connection. Furthermore, applying a corrosion inhibitor to wire terminations can help prevent corrosion and improve the connection's conductivity. Corrosion inhibitors create a barrier that prevents moisture and air from reaching the metal surfaces, minimizing the risk of corrosion. Apply a thin layer of corrosion inhibitor to the conductor before inserting it into the terminal. Regularly testing the resistance of electrical connections can help identify potential problems before they lead to failures. High resistance connections can indicate corrosion, loosening, or damage. Use a low resistance ohmmeter to measure the resistance of connections. Compare the measured resistance to the manufacturer's specifications or industry standards. Elevated resistance readings may indicate a need for further inspection and maintenance. Furthermore, implementing a lockout/tagout procedure during electrical work can help prevent accidental energization and ensure worker safety. Lockout/tagout procedures involve de-energizing the electrical circuit and applying a lock and tag to the disconnecting means to prevent it from being inadvertently re-energized. Ensure that all workers are properly trained in lockout/tagout procedures and that the procedures are followed consistently. Additionally, using arc fault circuit interrupters, or SIs, can help prevent electrical fires caused by arcing faults. SIs are designed to detect arcing faults, which are dangerous electrical conditions that can generate excessive heat and ignite nearby combustibles. SIs trip the circuit breaker when an arcing fault is detected, preventing a fire from starting. Consider using SIs in areas where arcing faults are more likely to occur, such as bedrooms and living rooms. Furthermore, using ground fault circuit interrupters, or GFCIs, can help prevent electrical shock hazards. GFCIs are designed to detect ground faults, which occur when electrical current leaks to ground. GFCIs trip the circuit breaker when a ground fault is detected, preventing a person from receiving an electrical shock. Use GFCIs in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor locations. In summary, preventing electrical connection failures requires a comprehensive approach that includes proper design, installation, maintenance, and testing. By following these recommendations, one can minimize the risk of electrical hazards and ensure the safe and reliable operation of electrical systems.